I want to do an example with capacitors in series and parallel. Here I have a system of 4 capacitors. I want to know what the equivalent capacitance is between A and B. And if I have a potential difference across A and B of 30 volts, I want to find what the potential drop is across the individual capacitors, as well as the charge being stored in the system and on the individual capacitors themselves. Okay, we're going to assume that I have labels here. The 16. We're going to say these are that our capacitances are all in nanofarads, and the labels and the numbers there refer to nanofarads. Okay, so the first thing we want to know is what is the equivalent capacitance of the entire circuit. So I have capacitors that are both in series and in parallel. In fact, if I had a single capacitor here in the middle, I'd simply have 3 capacitors in parallel. So I first want to combine the 2 capacitors in series here to an equivalent capacitor. That will give me 3 in parallel. So this intermediate step is I want an equivalent capacitance for these 2. Well, these 2 are in series, and so the equivalent capacitance for capacitors in series is given by this relationship where 1 over the equivalent capacitance is the sum of the inverse of the individual capacitances. And so I can go ahead and calculate that. 1 over 112 plus 1 over 1/16 is equal to 0.1458. There's a 3 repeating there. And then to get the equivalent capacitance, I have to invert that number, which is then 6.857. Always remember to invert. One error I see a lot of students do is they get this number and then they stop. They forget to, in fact, invert that to get the equivalent capacitance. Okay. And so now that we have the equivalent capacitance, we have this, we now have a system that looks like 3 capacitors all in parallel, where the one on the top is 10, the one on the bottom is 8, and one in the middle is this 6.857. So now we can go ahead and calculate the equivalent capacitance of 3 capacitors in series, and that equivalent capacitance, well, plus, is equal to just the sum of the individual capacitors in series. And so that result I can just look up and just do in my head. That's 24.86 nanofarads is the equivalent capacitance of the entire circuit. Okay, so now I have this entire system that's equivalent to a single capacitor with this capacitance. So now I can go ahead and ask the question, what is the total charge in the system? Because if I have a single capacitor, then the total charge in the system of a single capacitor is simply the capacitance times the voltage across it. And I have the equivalent capacitance. I know the voltage across it, which is 30, and so I can just go ahead and calculate this directly. And that's 745.8 nanocoulombs. That's this capacitance times the 30 volts across the system, because this is still A and B. So now I have the total charge of the system that's contained in the system, as well as the equivalent capacitance. Okay, but now let's ask the question that, okay, these individual capacitors themselves, what is the voltage drop across them, and what charge is being held on the individual capacitors? Okay, well, the first thing I can notice is that, well, this A is connected all the way here and all the way here, and B is connected by conductors all the way to those edges. So the voltage drop across the 8 nanofarad capacitor and the voltage across the 10 nanofarad capacitor is the same as the voltage drop across A and B, and that's 30 volts. So I can find the charge across those directly. So the 8 nanofarad, of course, has a voltage drop across the 8 nanofarad, which is equal to 30 volts. It's the same as from A to B. And then I can find the charge on the 8 nanofarad capacitor. That's 30 times the capacitance. This is the C times V, and so 240 nanocoulomb, because this 8 is nanofarad. I somehow wrote my N as a C. Okay, so 240 nanocoulomb is on the 8 nanofarad capacitor. So the other one I was looking at, that's up here, so that's 10 nanofarad capacitor. So the same thing applies. So I have my 10, my voltage across the 10 is the same 30 volts, and so I have the charge across the 10, which is just the voltage across times its capacitance. That's 300 nanocoulombs. Okay, so I know the total charge here, and I know the charge across each of the 8 and the 10, so that tells me I know the charge that's being contained in the middle branch of the system. And so if I look then here, the amount of charge in the middle, that's equal to the total 745.8. Can you see that? That's here, minus 540, and that's equal to 205.8 nanocoulombs. And so we know that this Q in the middle is on each capacitor. So if we look, if we call this the A positive and B negative, there's sort of QM on one side of the capacitor, the negative QM on this side, plus QM on this side, and minus QM on this side. And so the amount of charge in the capacitor that we talk about being stored is this amount QM, and it's on each side of the capacitor. So this is the amount stored on each capacitor in the middle, and then we can calculate the voltage drop across each of those. The voltage drop across the 12 nanofarad capacitor then is just 205.8 divided by 12, using the same relationship again over and over. And so the voltage drop across that is 17.15 volts, and then our voltage drop across the other one, the 16, is simply 30 minus this, which is 12.85. I might check that against this 205.8 nanocoulombs divided by 16, because that should also give us the same result, and we check that and it does.